Okay, so much like the first derivative number line shows intervals of increasing and decreasing and relative extrema, the second derivative number line will show us intervals of concavity and points of inflection. The values that go on the second derivative number line are critical values of f prime of x, or in other words, where f prime is undefined or equal to 0. Just as before, we choose intermediate points to identify the positivity and negativity of the interval, but those signs have different meaning this time. Positive values indicate that the function is concave up, and a negative sign indicates that the function is concave down. For example, let's look at the function x squared plus 1 divided by quantity x squared minus 4, as shown at the right. The derivative using the quotient rule is as shown, negative 10x over the quantity x squared minus 4 squared. The second derivative using a combination of quotient and chain rules is as shown here, after some significant algebraic simplification. So it follows that f prime of x cannot be equal to 0, because this portion, the 3x squared plus 4, will always be greater than 0. But we can see that because x squared minus 4 will equal 0 at x is equal to plus or minus 2, then we end up with the second derivative line for this function as shown. And as we can see in the graph, because our second derivative is positive here, we are concave up here and here, and we're concave down here. But a point of inflection will occur at changes in concavity, but only when that value is in the domain of the original function. So if we look at the number line, it'll appear that there's a point of inflection at x equals -2 and +2. But when we realize we go back to the original function, we can see that the function is not defined at x equals +2 and -2. So therefore, we don't have a point of inflection. Okay, so let's go ahead and take a look at example 1, and we're going to determine the intervals of concavity as well as the ordered pairs that represent the points of inflection if they exist. So for our first function, we need to first find our first derivative. So f prime of x is 3x squared minus 4x plus 1. Then find our second derivative, which is 6x minus 4. And then just as we did with the first derivative, we're going to set f double prime of x equal to 0, or f double prime of x undefined. So we can quickly see that this function is never undefined. So to set the second derivative equal to 0, we set 6x minus 4 is equal to 0, which gives us a critical value of x equals to 2/3. Now to find the ordered pair, we simply substitute in our function. And we have that f of 2/3 is going to be 8 over 27 minus 8 over 9 plus 2/3 minus 30. Okay, so then when we substitute in f of 2/3, we end up with -808 over 27. No, this is not one that I would expect you to be able to do without a calculator. We're going to evaluate this at f of 2/3. This is going to be our second derivative test. And we can see that when x is going to be less than 2/3, that the function will be concave down. And when x is greater than 2/3, the function will be concave up. So we can see that the function is going to be, so f of x is concave up from 2/3 to infinity because f double prime of x is greater than 0, and f of x is concave down from negative infinity to 2/3 because f prime of x, double prime of x, is less than 0. So after we have the concavity, we can see that f of x has a point of inflection, POI, at 2/3 negative 808 over 27 because f double prime of x changes signs. All right, so let's go ahead and take a look at example C. We'll skip over example B, and that will be a question at the end of this video for you to solve. So again, we need to start first with our first derivative. So s prime of theta, we know the derivative of tangent theta is secant squared theta. And we can see that we're going to restrict our domain from 0 to 2 pi. Our second derivative will be 2 secant theta times the derivative of secant theta, which is going to be secant theta tangent theta. So we can simplify this to 2 secant squared theta tangent theta. So we're going to set s double prime equal to 0, or s double prime of theta undefined. So here we're going to have some points where it's going to be undefined or equal to 0. Now, in order to help us, we can remember that we can rewrite 2 secant squared theta tangent theta as 2 times the sine of theta over the cosine cubed of theta. So from there, we know that s double prime of theta is going to be undefined when cosine cubed theta is equal to 0, which happens when theta is equal to pi over 2 or 3 pi over 2. We know that s double prime of theta equals 0 when theta is equal to sine theta is equal to 0, which happens when theta is equal to pi. It doesn't include 0 or 2 pi. Okay, so now that we have our possible points of inflection, we're going to go ahead and put our number line in here. And we have pi over 2, pi, and 3 pi over 2. And again, we know that our domain is restricted from 0 to 2 pi. And this is s double prime of theta. So as we look at this, we know that our function is undefined at pi over 2 and 3 pi over 2. So these cannot be points of inflection. We know that these are going to be asymptotes. And if you remember tangent theta is the same as saying sine theta over cosine theta. So we know that the function is undefined at pi over 2 and 3 pi over 2. So now as we go on through, we know that if we look at s double prime of theta, we know that we're going to have a positive function when theta is between 0 and pi over 2. So that means my function is concave up. Between theta is pi over 2 and pi will be concave down. Between pi and 3 pi over 2, again, we're going to be concave up. And between 3 pi over 2 and 2 pi, again, we're going to be concave down. And this tells us then that at pi is where we have our point of inflection. If we substitute in, so s of pi, we know that the tangent of pi is going to be 0. So there's our ordered pair of our point of inflection is going to be pi 0. So from here we have that S of theta is concave up on 0 to pi over 2 and pi to 3 pi over 2. S of theta is concave down on pi over 2 to pi union, and that's how I should have written the top one, 3 pi over 2 to 2 pi. And S of theta has a point of inflection at pi 0. Okay, so we'll go ahead and get example 2 started, and then I'll have you finish it up as part of your questions in the video. So we're going to start with f prime of x. We want to determine the increasing and decreasing intervals, relative extrema, intervals of concavity, and points of inflection for the function below. So f prime of x is going to be x cubed minus 2x squared plus x. Now we need to, in order to find our increasing and decreasing, we need to go ahead and set this equal to 0. So f prime of x is equal to 0, or f prime of x undefined. We know this never happens because it's a polynomial, and we have to factor this, which means we have x times x minus 1 quantity squared is equal to 0, which means we have critical numbers of x equals 0 and x equals 1. And from there, I will let you finish to find the increasing and decreasing. And then let's go ahead and find our second derivative. So our second derivative is going to be 3x squared minus 4x plus 1. And again, we want to set this equal to 0 or find where it's undefined. Again, we know that this never happens because it's a polynomial. And then when we factor this, we end up with 3x minus 1 times x minus 1 is equal to 0. So we know that we have critical values at x equals 1/3 and x equals 1. So I will leave this to you to go ahead and find the intervals of concavity as well as the points of inflection.